So welcome to today's session on two-ray model. So two-ray model is also called as ground reflection model. So this two-ray model is used to predict the path loss between your transmitter and receiver. Here this two-ray model is based on geometric optics. So two-ray model considers both your line of sight path and the ground reflected propagation path between your transmitter and the receiver. See here in the diagram, if you can see, so this is your transmitter and the receiver. So this two-ray model considers both the direct path, that is your line of sight path, and also a ground reflected path. Okay, so two-ray model is accurate to its maximum result only for the large scale signal strength over a large distance, that is for several kilometers, and also for the tall towers, right? So this is your the electric field for a line of sight signal is your ELOS, and for the ground reflected it is also called as ER or EG. Okay, so it is consisting both waves, that is overlapping wave at the receiver. One is your direct path and another one is the reflected wave from the ground. So the total electric field, the total received electric field T total is the resultant of the direct line of sight component ELOS and the ground reflected component EG. So by seeing the diagram, we can see here HT refers to the height of the transmitter and HR refers to the height of the receiver. Okay, and E0 is the free space electric field in volt per meter at the distance D0 from the transmitter to the receiver. That is for D greater than D0, and this should be greater than your Fraunhofer distance. So here the free space propagating electric field. Okay, free space propagating electric field E, it is a function of distance between your transmitter and the receiver with the time t. It is given as E0 D0 by D cos omega c into t minus d by c. That is for a transmitting distance d greater than D0. So the envelope of the electric field at d meters from your transmitter at any time t is this. This is your envelope. Okay, E D0 D0 by T, that is the envelope. Okay, so the two propagating wave arriving at the receiver, one is your line of sight wave which travels. So here if you see in this diagram, so the one which is traveling, that is this line of sight wave, travels at a distance d dash, and the one which is traveling here, that is your ground reflected wave, that is traveling at a distance d double dash. So two propagating wave arrive at the receiver. One is your line of sight wave, another one is the ground reflected wave. This line of sight wave travels at a distance d dash, and this ground reflected wave travels at a distance d double dash. Okay, so as you know, your total electric field is ELOS plus your ground reflected, right? So I can just replace by this distance. So if it is because of your ELOS, I can replace this d by d dash, and if it is because of your ground reflected, I can replace this d by d double dash, right? So in this equation, right? So the total electric field is ELOS plus your EG, right? So here in the distance I have replaced it by d dash, and here the distance I replaced by d double dash. You can see here replaced by d dash and replaced by d double dash for your ground reflected signal. And one more thing here we have to see is, according to the law of reflection, that is in your dielectric, right? So if this is the scenario, let us see, this is your incident wave and this is your reflected wave. Okay, so electric field of your incident is EI and the electric field for the reflected is ER, or it is also equal to EG. Okay, and this is the theta I and this is theta R. So according to the law of reflection in a dielectric, your theta I is equal to theta r, and also your ground reflected electric field Eg is equal to tau into Ei. Okay, so what is this tau? This is the reflection coefficient for ground, right? So for ground it is 1. Okay, so how I can write my E total? E total is equal to ELOS plus EG, right? So for this it is line of sight, so it is incident plus tau into EI. So if I take it in common, so EI 1 plus tau, so that is going to be my E total, right? Right. So for small value of this theta I, right? So for small theta I, the magnitude of your reflected wave is almost equal to the incident wave, right? Almost equal to the incident wave. That is, your Eg is equal to your Ei. Okay. So almost equal to the incident wave, but only thing is it is out of phase. Phase is 180 degree, right? That is why we can say the magnitude E total is equal to ELOS plus EG, because the magnitude is almost same for your theta I, small theta I. That is for your gazing incident theta I, the reflected wave is almost equal in magnitude and out of phase with the incident wave. Okay, and so this is the total electric field. And now you have to find out the path difference between your line of sight and the ground reflected path, and that is expressed by this equation. So this is using the method of image. So to find out this D dash, okay, see here. So this is your transmitting antenna height, and this is your receiving antenna, transmitting antenna height and receiving antenna height. So what would be this height? So this is HT minus HR. What would be this height? So it is a mirror image. Okay, so this is HT means this is also HT. This is HR means this is also HR. And so what is this total height? So this is HT plus HR, right? So this distance is equal to this HR. So HR plus HT is the distance from here to here. Okay, so to find out this D dash and D double dash, so distance traveled by line of sight is D dash and the distance traveled by the reflected is D double dash. So to find out this D dash and D double dash, so we have to use this method of images. So now using the Pythagoras theorem to find out this D double dash, we can use this small triangle. Okay, so this triangle. So D dash is equal to square root of, so what is this? This side it is HT minus HR, right? Square root of HT minus HR whole square plus a D square. Why D square? Because this distance is D distance. Okay, and what is D double dash? So D double dash, if I take the mirror image, so this distance is equal to this. Okay, so I am going to take the bigger triangle, this triangle. Okay, so what is the side here? HT plus HR, right? So it is square root of HT plus HR whole square plus this is D square. This one is D square. So the path loss is, or the path difference is, del is equal to D double dash minus D dash, right? So do you understood this? So I can tell you here. So this is like this, right? Mirror image. So this height is ht and this height is hr. So the same thing, this is hr and this is ht. And this is my reflected wave. So this is d dash and this reflected wave distance is d double dash. Okay, so for finding d dash, so I will use this triangle. Okay, this triangle. Okay, so this height is hr till this. Okay, from this to this height is hr. And what about this? The total height is ht. So this becomes ht minus hr. Okay, so I can find out the distance, right, by using the Pythagoras theorem. So for this triangle, okay, what is this distance? It is the distance traveled between the transmitter and the receiver. So d dash is square root of ht minus this one, ht minus hr whole square plus this d square. And what about d double dash? So d double dash, this one. Okay, so when you are taking mirror, so this distance is equal to this distance. Okay, now I can take which triangle? I can take this triangle. Okay, so what is this height, total height? So this is from here to here, it is ht. So from here to here it is hr. So what is this total? So it is ht plus hr. And you know this distance is d. So it is equal to ht plus hr whole square plus d square. Right? Okay, so the path difference is d double dash minus d dash. So if you solve, it is approximately equal to 2 into ht hr by d. So once the path difference is known, the phase difference, so you know the path difference now. So once the path difference is known, the phase difference theta del between your two electric field components and the time delay tau d between the arrival of two components can easily be computed. Okay, so your phase difference theta tau is equal to 2 pi del by lambda. So lambda, you know, it is omega lambda c by f. So this is 2 pi del c by f. If f is going up, so 2 pi f will become your omega c. So omega c into del by c. So this is going to be your path difference between two electric field. And your time delay between the arrival of two different components, that is because of your ELOs and because of your EG. So tau d so your tau d, it is del by c. So I can just substitute this. So it is theta del by 2 pi fc. So one more thing here to be noted is when your d becomes large, the difference between your d dash and d double dash becomes very small, and the amplitude of ELOS and EG are virtually identical, only differ in the phase that we know, right? That is when your d becomes large. Okay, so the distance between the difference between your d dash and d double dash becomes very small. Okay, and amplitude of your E, LOS and EG are vertically identical, visually identical, and it differs only on phase. So because of that only we can write it like, we can write like E0 D0 by D, it is approximately equal to E0 D0 by D dash, which is approximately equal to E0 D0 by D double dash. And if the electric field is evaluated at T is equal to, suppose if the electric field is evaluated at T is equal to D double dash by C, then it is represented like this. It is all mere substitutions. You can do substitutions, and finally you have this E D dot by D into cos theta del by theta del minus 1. Okay. All right. So your E total. So as previously I said that if your distance between your transmitter and the receiver is very large, then we can say your D dash is approximately equal to D double dash, and because of that we said your magnitude of all is almost equal. Okay, magnitude is same, but it differs in the phase. And the receiver electric field at T is equal to D double dash by C. Okay, that is your reflected distance, right? So if this is the case, then I have to just replace it, and if I compute it, it becomes like this. Okay, so this is going to be your E total. So this is the distance D. Okay, so if I compute it, E total is going to be 2E. If I take all this out, it is going to be 2 E naught D naught by D sine delta by 2. So this is your electric field. And for theta del by 2, if you replace your formula, then I'm getting this E total as this. Okay. So the magnitude with respect to a reference of, that is E0 is equal to 1 at a distance D100. So the near 100-meter signal can be stronger than the E01. The second ray adds an energy that would have been lost otherwise. So for the large distance, what it should be? It should be greater than HT into HR. Okay. So here in this, if just mere substitution of this delta D, then it becomes like this. So your received power is PT GT GR HT square and HR square by D power 4. So it is inversely proportional to the power of 4 distance. So when I write it in dB, so this equation, when I write it in terms of dB, it is 40 log B minus 10 log GT plus 10 log GR plus 20 log H square, no, HT square and HR square. So 20 log HT, 20 log HR. Okay. So now it is D power 4 instead of free space. For free space it is D square, and for this two-ray model it is D power 4. So your receive power is D power 4 times. Thank you.